I think I'm recording now. Okay. Yeah, I was saying, yes, in a previous section, we discussed different measure of variation or measure of spread, like the standard deviation, the variance, and then we had the coefficient of variation, right? And then we discussed the Chebyshev theorem. Right, so now in this section 4.1, so this is about the scatter diagram. And linear correlation. All right, so let me just remind you the problem here, what we are doing in this section, right? So we have data, and the data is actually represented by pairs or by two variables, not just one variable, but two variables, X and Y, right? So, and we had an example, I think from the last week. Let me just write down the example we had. So, so we have the following data. So the data here represents so we had like two variables, right? So we had the X variable, and we said the X variable represent the magnitude of the earthquake. So X is the magnitude. Right, of course the unit here, it's the Richter. And then we have a second variable, so the variable Y, and the variable Y we said represent the depth of the earthquake, right? That's the depth in kilometers, let's say. In kilometers. This is in kilometers. Anyway, so the question was, so the goal here is to see if there is any relationship or correlation or connection between the magnitude and the depth of the earthquake, right? That's the goal here. So the question is there any relationship or correlation? So again, correlation means like a relationship or connection. That's another word for correlation. Connection between the X, which is the magnitude of the earthquake, right? And then the Y, which is the depth. All right, so that's what we are doing here. We are trying to answer this question, right? And again, the data, it's given by, so we have a sample of how many earthquakes? We have like 7. So we have like 7 data pairs, right? So we have so this is your X, Y. So for the first earthquake, the magnitude is 2.9 Richter, right? And the depth is like 5 kilometers. Okay, so this is, again, this is like for my first, this is like my first earthquake. Okay, my second earthquake, we have the X is 4.2, I think, Richter, and then the depth is like 10 kilometers, etc. Then we have like third earthquake, we have 3.3 and 11.2, 4.5, and the corresponding depth is 10 kilometers, 2.6, and then 7.9, and then 3.2, and then 3.9, and then for the last earthquake we have the X, the magnitude is 3.4, and the depth is like 5.5. Okay, All right, so again, as I said, we are trying to see if there is any correlation, connection between the magnitude and the depth, right? Given this sample, right? We have a sample of, we have like 7 earthquakes here, and we are trying to see if there is any relation between X and Y. All right, so we're gonna focus on one kind of relation or correlation called the linear correlation. Okay, so what's a linear correlation? It's just a straight line relationship between the two variables. Okay, this is the straight line, straight line relationship between the variables X and Y. Okay, and the thing is, so when you have like this relationship between the two variables, it means that the two variables actually they change at a constant rate. Okay, that's what it means. It means that the two variables, so the variables X and Y, they change. The variables X and Y, they change at a constant rate. Right. So we discussed last week how to represent the data using the scatter diagram. You know, if you have, so to represent the data, so we use the scatter diagram. Scatter diagram. So whenever we have like two variables, X and Y, then use the scatter diagram to represent the data diagram. Okay. And in the scatter diagram, of course, we said we're going to have like, you know, two axes. There will be this like the horizontal axis, which is the X axis. Right. And then there will be like a Y axis. Okay. And the idea, of course, is to plot your data pairs, right? So you need to plot data pairs X, Y, X and Y. Okay. So for example, just to show an example here, for example, if my X is, so if my X is 2.9, then the corresponding Y is 5, right? So what we do to represent this this pair of data, 2.9 and 5, so your X is 2.9, so somewhere here, let's say this is 2.9, this is your X equal to 2.9, right? And then here on the vertical axis, your Y is 5, okay, right? Right, when your X is 2.9, then Y is 5, right? So then the corresponding point would be this one right here. So then you get this point here, right? So that will be the corresponding point. Okay. Now, so you plot all the data pairs, right? And you get what we call the scatter diagram. And now the thing is, you need to check if your scatter diagram or your data resembles a line. Okay. So if the data resembles a line, then you have a linear correlation. That's what I call a linear correlation, right? So you have your scatter diagram. So you plot all those data pairs, right? So I don't know, like the next point would be like somewhere right here, another point right here, you know, and then another point right here, etc., right? And of course, the best line that fits the data is the line that comes closest to each point, right? So for example, here, let's say the best line that fits the data here would be this line, for example, here, okay? And so here, again, it's not all the points, I mean, not all the points they lie on this line, but I mean, they are very close to this yellow line, right? So in this case, we have, I mean, your scatter diagram looks like it's a straight line, right? So in this case, we have a linear correlation. So this is, so if the scatter diagram looks like a straight line, okay, then we have what we call, then we have a linear correlation or linear relationship, right? So a linear correlation. Okay. Of course, in some cases, your data doesn't resemble a line. So for example, example 2. So let's say you graph your scatter diagram, and then you have your x, you have your y-axis, etc., and then you plot all the data pairs, and you get something which looks like you don't join the points, right? They're just so you take your points. So for example, let's say you have all these points here. Okay. So like in this example, as you can see in this example, I mean, the data doesn't resemble a line, right? Because, you're supposed to take a line which is kind of close, the closest to each point, right? But I mean, if you, for example, if you say, well, if you take, for example, this line right here, then you're going to have some points which are kind of, far from the yellow line, right? So, I mean, in this case, you don't have, I mean, your data doesn't really resemble a line. So this is not a linear correlation. So so here in this example, there is no linear correlation.
Excuse me, Professor.
Yes,
So
yes.
that means I can, let's say the coordinations are matching, let's say at the end. It doesn't matter where I place the line, as long as something is connecting.
Yeah, it doesn't matter. Yeah, it doesn't matter. So actually, of course, so if all the points they lie on the same straight line, then you would have like what we call a perfect linear correlation, right? So so in this next example, example 3. So this is yours, let's say your scatter diagram, so X and Y, and then let's say here's your data. Okay, so like in this case, all the points, they're gonna lie on the same line, like on the same straight line. This one here, right here, right? Okay, so this is what I call a perfect. This is a perfect linear correlation. Because, well, all the points, they lie on the same line. Now, I mean, this doesn't really happen all the time. So if on the same line. So for example, now, if you have like a couple of points which are kind of not really far, but kind of close to your line. So for example, example 4. So example 4. So like you have like X, this is Y, right? And then suppose you have like a point like well, the first 2 points that lie on straight line, but the next is it's kind of close. Like if you take, let's say, for example, again, this is just an approximation. I mean, as I said, the best line here is supposed to be the line that comes closest to each point. But I mean, it's just like a kind of a guess here. But let's say here's your line, the best line that fits the data. This one here. Okay. So like you have like 4 points. So like this one here, these 4 points, they lie on this line, this yellow line. But you have these 2 points, like this one here, right? This one and this one, they are kind of close to the line, right? They don't lie on the line, right? They don't belong to the line, but they are kind of very close, right? So this is not a perfect linear correlation, right? Because those 2 points, they don't lie on the line, but it's a linear correlation. It's still a linear correlation because your points, these 2 points, they are kind of very close to your line. Okay, so that's why I call it linear correlation. Okay, so this is an example of, again, this is an example of linear. But then if you have like a mess of points, like, you know, if you have like something like a, you know, just the points are kind of, you know, kind of random. The position of the points are very random, you know, like this here, you know. So it doesn't really look like a line, right? I mean, if you take if you take, let's say, this line right here, well, you have a bunch of points which are like kind of far from your line. Okay. So the idea is, like in this case, it doesn't look like you have a line here. Okay. And that's what I call, so in this case, we don't have any, there's no linear correlation. You see the difference? So this is so in this case here, there's no linear correlation. So you see the difference, guys, between the linear correlation and no linear correlation? Like in this case, we have like a mess, right? It's like the position of the points are kind of random, right? It doesn't look like they are on the same line. And that's different from this example here, right? This example, they are, you know, there are some points that are not pretty close to your line, but still they are not far. Anyway, we're gonna have like a numerical measurement to see if we do have a linear correlation or not. Okay, so I mean, it's not really a guess, because we're gonna have like, we're gonna compute something which is actually called the correlation coefficient, and with the correlation coefficient you can determine if you have a linear correlation or not. Okay, so it's not really a guess, but I'm just saying, like, from the graph you can make an educated guess. From the graph you can say, you can see if you have or not a linear correlation, right? But as I said, like later we're gonna have in a minute, we're gonna have like a measurement, a numerical measurement, and number, and then that number would tell you if you do have or not a linear correlation. Is there any question, guys? I mean, just from like, again, just from the definition of this linear correlation, does it make sense to you? All right. I don't think there are questions. All right. So and of course there's I think I mentioned this last week, but there is what we call the positive linear correlation, when your line goes up and when your line goes down. That's what we call negative linear correlation, right? Yeah, I'm going to just remind you. So so there are two sorts of or two kind of two linear correlations. So first we do have the positive one. So positive linear right? So this is when your line goes up So like here in this case, my data resembles a line. So and this would be actually a positive. This is a positive because the line goes up, right? And then of course, then we have a negative 2. We have a negative linear correlation, and this is when the line goes down. It goes down, right? So in this case, so we're gonna have something which looks like right, something which looks like this here. Example like this, right? And so in this case, we have like we have a negative negative linear correlation because the line, of course, goes down. Because the line goes down. All right. So as I said, now what we're going to do, we're going to compute a numerical measurement. And actually, this numerical measurement is going to describe the strength of your linear correlation. Okay, so this numerical measurement is going to say if you do have a linear correlation or you don't have a linear correlation. Okay, so so next I'm gonna discuss, and then I'll get back to our example with the magnitude and the depth of the earthquake. Okay. But yeah, so let me first talk about this numerical measurement of the correlation here. So so next, so let's discuss the sample, the so-called sample correlation coefficient. Okay, so this sample correlation coefficient is going to be a number, and as I said, with that number, you can see if you can check if if you do have a linear correlation or not. Okay, so the sample, so this is a definition, let's say. So the idea here is that the sample correlation coefficient is a numerical measurement. Sample correlation coefficient is denoted by R. So it's denoted by R. Okay, and this is a mathematical or numerical measurement. This is a numerical measurement. And this numerical measurement is going to describe the strength of your correlation. So this describes this numerical measurement that describes the strength of the strength of the linear correlation between between the variables x and y, right? Between the variables x and y. Okay, so this number R, this sample correlation coefficient, this number R has a couple of properties. So this number, of course, I'm going to show you how to compute this number. But first, let me just say, so this number is going to be always between -1 and +1. So like if your answer is not between -1 and +1, then it means you made a mistake. So the properties of this R, so properties, and then I will show you how to compute this number R. Okay, so properties of R. Again, R, this is what I call the sample correlation coefficient. So first, this number R is always between -1 and +1. It's a number, so R is always between -1 and +1. Okay. If R is equal to +1, so if R is exactly equal to +1, then actually you have a perfect linear correlation. Okay. Then we have a perfect linear correlation. Again, what I mean by perfect linear correlation is that your all the points of your data, they're gonna lie on the same line, right? This is what I mean by, again, this is what I mean by perfect linear correlation, right? So all your points, they're gonna belong to the same line. They lie on the same line, okay? So if your number R is +1, it's actually a perfect linear correlation. Same thing, if R is -1, so we also have a perfect, linear correlation. So if R is positive or -1, then you do have a perfect linear correlation, okay? Now, if R is close, very close to +1 or very close to -1, then the relationship between X and Y is close to linear. It's almost linear. I mean, it's not perfect, perfect linear correlation, but it's very close to linear, okay? So if R, so if this number R, and as I said, I'm gonna show you how to compute this number R in minutes. But if this R is close, very close to +1 or -1, okay, then the relationship between X and Y is close to linear. Then the correlation or the relationship between X and Y, correlation of the relationship between X and Y, it's not perfect. It's not a perfect linear correlation, but it's very close to perfect, right? Is close to a perfect linear correlation. Okay. Now, if R is, so 2. So this is when R is positive or -1, or it's very close to positive or -1. Now, if R is close to 0 or equal to 0, then you don't have, there's little or no linear correlation. So if R, so if this number R, if R is close, is equal to 0 or close to 0, very close to 0, then there is no linear correlation. Okay. Now, so if you're close to 0, very close to 0, it means there is no, you don't really have a linear correlation, right? if you are close to, your number is close to positive or -1, then you are close to a perfect linear correlation. Now, if R is positive, there's a difference between positive R and negative R. So if R is positive, it means you have like positive linear correlation, right? Like your line is going to go up. If R is negative, okay, then you have a negative linear correlation. So in other words, your line is going to go down, okay? So so if R is positive, so if R is positive, then we have a positive correlation. We have a positive linear correlation. Okay. Positive linear correlation means, as I said, the line is going to go up. It means that as x increase, the y increase. Okay, as x, variable x, as x increases, y increases. Okay. Now, if R is negative, then that will be a negative linear correlation, right? And as x increases, y is going to decrease. So if R is negative, then we have a negative linear correlation. So if your data looks like resembles a line, then your line is going to go down, right? So as x increases, y decreases. Okay. So I mean, again, the idea is the following. So what you need to keep in mind, guys, is the following. So like you're gonna have like 3 or 4 cases. So if R is equal to 0 or R close to 0, then your scatter diagram. So you don't have a linear correlation, right? So then your scatter diagram would be like something like this here. Okay, your data doesn't resemble a line. Okay, there is no linear correlation. There is no linear correlation or relationship between x and y. Okay. Now, if R is equal to positive or -1, right? Then you have like a perfect linear correlation, right? This is a perfect. So all your points are gonna belong to the same line. Okay, so we have a perfect. This is a perfect linear correlation. Now, if you are close to positive or -1, you are close positive or -1, then it's not perfect, but still you do have like a linear correlation. So the graph or the scatter diagram would be like something like this here. So then you'd have like something, so your data is going to look like something like this here. Okay, so it's not, I mean, it's not perfect, but still this is a linear, so this is linear correlation. Okay. And of course, here there are like two cases, right? If R is positive, then so in this case, this is positive linear correlation, right? And there's the other case when R is negative, close to -1. So you'd have something like this here. So your data is going to look like something like this. Right. So here we have a negative. This is a negative. So your R is going to be close to -1. So this is a negative linear correlation. Okay. So that's like the properties of this number R. Now I'm going to show you, of course, how to compute the formula for R, how to compute R. The formula is not simple, I would say, but so I'm going to try to, yes, I'm going to split like the formula into like a couple of steps. Okay. But first, is there any question, guys, about this, the properties of R? I mean, I hope you see that. Yes.
How come it's called R if we have the x-axis and the y-axis? Why is it R?
Well, I mean, so from the graph, as I said, so from the graph, you can make like an educated guess. You can say, well, you take a look to the graph, and then your graph is going to resemble a line, for example. Then, yeah, then you can say, well, you have a linear correlation, right? But we're going to also use this R to make sure that your graph is correct. To make sure that, yes, so your R is going to be close to 1 or close to -1. So it's just to make sure that your substance, your graph is correct, that you do have this linear correlation, right?
Okay, so when we're graphing the linear correlation,
yes.
that's what you call R.
No, the R is going to be a number. So I'm going to show you in a minute.
Oh, okay. I'm sorry.
No, I'm going to show you in a minute how to compute R. But all I'm saying is, example, let me just, like, I have this graph. I have these points like this. Okay. Okay. So like in this case, my data looks like resemble a line, right?
Mm-hmm.
So a guess here would be to say, well, we do have a linear correlation, right? But first, I'm gonna compute R just to make sure that it's correct. Okay. But
I follow. Yeah. I follow you now. I got you.
Okay. So now I'm gonna show you how to compute this R. All right. All right. So now let's compute R. Okay. Well, so we have two variables, right? We have this X and we have a Y. So I'm gonna do an example, okay, numerical example, and the same step. I mean, at the same time, I'm gonna use the example to show you the steps, okay? So example. So this is an example, but it's at the same time, it's a definition. All right. So we have this example, another example with the muggings in Boston Park. In Boston's Park. All right, so we have a 10 days sample, and X, the variable X, gonna represent the number of police officers on duty. So this is the number of police officers on duty that day, right? And the variable Y is going to represent the number of muggings that day. Okay, and of course, the question is there a relation between the number of police officers on duty and the number of muggings of that day, right? So the question is there a correlation or a correlation between the number of the number of police officers and the number of muggings that day. Okay. Now, let's say we have the following data. So as I said, we have a 10 days sample, right? So so like first day, let's say in the first day we have 10 police officers on duty, okay? And the number of muggings that day is 5. Okay, that's 5. Next day, second day, we have 15 police officers on duty, okay? And then we have just 2 muggings that day. Third day, we have, let's say, 16 police officers, just 1 mugging. Next day, we have just one police officer on duty, and then 9 muggings. Then next day, we have 4 police officers, 7 muggings, 6 police officers, 8 muggings, and then 18 police officers, and just 1 mugging. 12 police officers, 5 muggings that day, 14 police officers, and 3 muggings. And then last day, we have 10 days as a sample, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th day, we have 7 police officers on duty and 6 muggings that day. This is 14, of course. This is 14. Okay. All right. So again, I want to answer this question: if there is any correlation or relationship between the number of police officers on duty and the number of muggings. Okay. So, well, first question. Of course, you can make a scatter diagram. So let's, let's compute R. Okay, so let's compute R. So this is the sample correlation coefficient. Okay, so first we are supposed to compute the sum of the x's. So step 1. So we are supposed to compute the sum of the x's. So step 1, that would be the sum of the x's. Okay. So the sum of the x's is denoted by summation. So this is the sigma, capital sigma. So it's a sum of the x's. So you take just the x values, right? Like the first x value is 10. Plus the second x value is 15, plus 16, plus 1. Again, I'm taking just the sum of the x values, right? There's 10, 15, 16, 1, plus 1, plus 4, plus 6, 17, plus 12, plus 14, and then plus 7. Okay. So that's the sum of the x's. So in this case, the sum would be 103. Okay, that's supposed to be your first step. Sum of the x's. Now we do the sum of the y's. So step 2, we need sum of the y's, the y variable, right? So again, it's a summation, so sum of the y's. So first y is 5. That's the number of muggings, right? So it's 5. Second day we have 2 muggings plus 2. Third day we have 1 mugging plus 1, plus 9, plus 7, plus, again, this is the y values, plus 8, plus 1. Next there's 5, then there's 3, and then there's 6. So sum of the y's. So in this example, that would be 47. Okay. So we have the sum of the x's, sum of the y's. Now we need the sum of the x squared. So step 3. Step 3. So step 3, we need the sum of the x squared. Okay. So what's the sum of the x squared? So what we do is we take the square of this first number, the first value of x. So like the first x is 10, right? So that's like 10 squared plus second value of x is 15. So we need 15 squared plus 15 squared. Next value of x is it's 16. So it's plus 16 squared. Plus next value of x is 1. So that's plus 1 squared, right? Plus 4 squared, etc. Okay. So you take the square of x. So here, again, the square, it means you multiply the number by itself. Like 10 squared, that's like 10 times 10, right? 15 squared, it's like 15 times 15, right? Etc. 16 squared, it's 16 times 16. Anyway, so 10 times 10, that's 100. That's 100, right? 15 times 15, that's 225, right? Plus 225, etc. Plus 16 times 16, right? Etc. So here, the sum of the x squared, I mean, if you, of course, you need to take the sum of all the x squares. So the answer here would be 1347. 1347. Does this step make sense to you guys? Do you see what I mean by the sum of the x squared? You see the numbers here? So you take the 10 plus the 15 squared plus the 16 squared plus 1 squared plus 4 squared, etc. Now next, of course, you're gonna do the same with the same thing with the y. So step 4, we're gonna need the sum of the y squared. Step 4. So we're gonna need the sum of the y squared, right? So this is denoted by capital sigma. That's a summation symbol. Sum of the y squared. So you take the first y and you square it. So first y is 5. So we have next y is 2. So that's plus 2 squared. Next y is 1. That's 1 squared. Next y is 9, right? So we have 5, we have 2, then 1, 9, 7, etc., right? So after 1, we have 9. So that's plus 9 squared. After 9, we have like, I think 7. So that's 7 squared, etc. Okay. So then sum of the y squared, 5 squared, it's 5 times 5, right? Again, the square, you need to multiply the number by itself. So it's 5 times 5, right? Which is 25, plus 2 squared, that's 2 times 2, that's 4. 1 squared, that's like 1 times 1, that's 1. 9 squared, that's like 9 times 9, that's 81. 7 squared, 7 times 7, that's 49, etc. Okay. And the answer here would be 295. So this is, well, some 295. Okay. There are 2 more steps. Well, right. So next step would be, so step 5, we need to multiply x by y and take the sum. So step 5, So, I mean, in the homework and the test, guys, because I mean, this is a lot of computation. I mean, this is kind of crazy, I would say, right? It's a lot. I mean, unless you have like a very small data, like you have like I don't know, 4 or 5 data pairs, but like here in this example, right, they have like 10, a sample of 10 days, right? So we have like you have like 10 data pairs, right? It's a lot. So I mean, in practice, like in the homework, in the homework or in the like in the test, I would just give you the answers, okay? The answers to these steps, okay? But of course, I mean, you can also have like in the homework question where we have to check or we have to do all these steps, okay? Anyway, so step 5, you need to multiply x by y and take the sum. So multiply multiply. So multiply x by y and take the sum. Okay, so that's like sum of x times y. So we multiply the first x by the first y. So like here, first x is 10, first y is 5. So that's like 10 times 5. So we have 10 times 5 plus next data pair. So we have x is 15, y is 2. So we need to multiply 15 by 2. So plus 15 times 2. Next data pair. So we have x is 16 and y is 1. So we multiply 16 by 1. So plus, plus 16 times 1. Next data pair is you have 1 and 9. So 1 times 9. So plus 1 times 9. Okay, etc. As I said, we have 10, a sample of 10 days, right? So you have like 10 data pairs. Of course, you apply PEMDAS rule, so you need to multiply x by, you need to do the multiplication first. So like here, 10 by 5, that's 50, plus 15 times 2, that's like 30, plus like 16 times 1, that's 16, plus like 1 times 9, it's 9, plus etc. Right? So you do the multiplication and then you take the sum. So then the answer in this example, the answer would be 343. Okay. Now the last step. So I'm going to use all these steps to compute my R. So step, let's say this is step number, well, actually the formula of R is it's kind of complicated. So I'm gonna split the last step like into 2 steps. So step 6. So in this step 6, we need to compute so we need to compute n times, so the n is the size of the sample. So we compute n times sum of xy minus sum of the x's times the sum of the y's. So this is, so the n, that's the size of the sample. So the number of data pairs, this is the number of the data pairs. Okay. Now, sum of x times y, this is from step 5. This is from this number here. This is from step 5. Step 5. Right. Now, on here, this is step 1, the sum of the x's. That's step 1. And then here, multiplied by, this is step 2. So like here in this example, the size of the sample, we have a sample of 10 days, right? We have 10 data pairs, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 data pairs, right? So n is 10. So here, so let's compute this. So n is 10 times the sum of x times y. So this is from the step number 5, x times y. We'll multiply x by y, right? In the step 5, we'll multiply x by y. And we got 343, right? So here, we'll multiply the 10 by 343 minus, and then we have this sum of the x's. Okay, that's from the step 1. Sum of the values of x, right? In step 1, we computed, the sum of the x's, the 10 plus 15, etc. So we got 103. So here minus, so 103 times the sum of the y's. So that's the sum of the values of y. That's step number 2. And we got 47, right? The sum of the values of y, it's 47. So here, multiply by 47. 47. Okay. So this is actually, so 10 times 343, that's 3,430. Okay. Minus, and then this is, let me see, this is equal to, let me see here, my note. So it's 103 times 47, right? So let me see here, times 47. So that would be equal to, 4,841. So then the answer to this step, so minus, so the difference would be equal to, this is equal to negative 1,411. Okay. I'm sorry, we are not done yet. So this is just a step number 6. So in the step number 6, this is like the top of the formula of R. Now the bottom of the formula of R, so step 7. Okay, so in this is step 7, we need to compute. So here, so we need to compute the square. So compute the square of, the square of, or square root, sorry, square root of the n. So n, so n times the square of the sum of the x square minus the square of the sum of the x's. Minus, and then the same thing with the square root, sorry, times, this is times here, and the same thing, we multiply. So compute this thing, and square root of, same thing as with the y variable, so sum of the y square minus sum of the y's square. So this is, all right, so let me just explain here. So the n, again, that's just the size of the sample. This sum of the x squared, this is from step number 3. Okay. And here is, just be careful, there's difference between the sum of the x squared and the square of the sum of the x's. So sum of the x's, that's from the first step. But then we need to take the square of the answer. That's from the step 1. Here, the same thing. So this sum of the y squared, this is a step 4. And the sum of the y's here, this is from step 2. So yeah, so let's just compute this thing here. So like for the first one, we have, there's a square root, there's n, there's a sum of x squared minus square of the sum of the x. So this is equal to the square root. There's this a huge square root. First, we have n, right? N, that's the size of the sample. We have 10 data pairs, or a sample of 10 days. So we have n is 10 times the sum of the x squared. We said that's from the step 3, right? This is from step 3, right? So let's just get the number from the step 3. That's 1347, 1347. So times 1347 minus, and then you take the number. So this is sum of the x's. That's from the step 1. This is from step 1. Okay. The sum of the x's. So this is step 1. We got let's see, from 103, right? But then, so it's minus 103. That's from the step 1, and then you need to take the square of this 103. So you keep the square root. So this is equal. So they keep the square root. Okay. So we have 10 times 1347. That's 13,470 minus, and then you do this 103 squared. That's 103 times 103. Okay. So that's equal. Let me see here. So 1 times 103. So that'll be equal to 10,609. Right. This is 103 times 103. Now you take the difference, the square root. That's the last thing you do. So you take the difference between the 13,470 and the 10,609. So that's square root of actually 2,861. Okay. And then you take the square root of this number. So square root of square root of 2,000. So square root of 2,861. Let me just find the answer. That will be equal. It's not here. Let me just check my. So square root of 2,861. So that will be equal to. So this is a 53.48. So this is for, again, so what we computed here, this for the x's. So what I'm saying here is that the sum of square root of n times the sum of the x squared minus the square of the sum of the x's. So this is actually 53.48. Now you need to do the same thing with the y. This is for the x. So we need to compute square root of n sum of the y squares minus square of the sum of the y's. So again, this is and that's the size of the sample. We have 10 data pairs. This is from the step. This is from step 4, and this is from step 1. Sorry, this is y here. This is a y. So this is from the step 2. Step 2. All right, so this is, in other words, this is the square root of, so again, n is just 10. Step 4, sum of the y squared. So step 4, we got 295. So that's 10 times 295. Minus, so from step 2, we got, step 2, where is step 2? We got 47. I know this formula it's actually a mess. It's complicated, but I mean, I will write down like the whole formula for R, but we'll see, like I mean, if you want to computer R, you have to really divide all the computations on those steps. So yeah, from the step 2, the sum of the y's, we said it's 47. So it's 47, and then we apply a square. Okay, so this is equal to square root of, so 10 times 295, that's 2,950, minus 47 square. So 47 squared, it's 47 times 47. That will be 2,209. You take the difference with the 2,950. Let's see. So this is actually equal to 741. And then you apply the square root. So the last thing to do is, again, it's to apply the square root. So this is square root of 741. So that's 27.22, I think. All right, now we can compute R. Sorry, I know this is a lot, but so this is step 8. So R, let me just give you the formula for R. You see from the formula, it's, so step 7, I think. This would be step 7, yes. All right, so step 7. So the formula for R is the following. So this is the formula of R. So R is actually equal to N, okay, and that's the size of the sample, times the sum of the X times Y, minus the sum of the X's times the sum of the Y's, right, over, there is in the denominator, we have the 2 square roots. So we have the first square root, this N times sum of the X squared minus the square of the sum of the X's times, and we do the same thing with the Y. So we have like N sum of the Y square minus the square of the sum of the Y's. Okay. So actually the top, we computed the top and the step, the top, that was step number, where's the top? Yeah, number 6, step 6, right? You see in the step number 6, we computed, you know, N sum of X times Y minus sum of the X's times sum of the Y. So that's from step number 6. And we got, so this is step number 6. This is step 6. Actually, this is step number 8 here. This is 8. Now the denominator, actually that's from the step, this is from the step 7. I have this denominator here. This is step 7. Okay. So in our example, so the top, which is from the step number 6. So in step number 6, we got this negative 1411. So negative 1411 over. Now we have from step 7, so we have this square root of N sum of the X squares minus the square of the sum of the X's. So that's this number right here. That's 53.48. So this is for 53.48. 53.48 times. Now we did the same thing for the Y, right? So when we did the same thing for the Y, we got, here's the formula for the Y. So we got this 27.22. So it's times this 27.22. So 27.22. So this is negative 1411 over. So you multiply this 27.22 by the 53.48. And so if you multiply the bottom, that's actually a 1455.79, I think. Now you divide, it's negative 1411, right? So it's negative 1411 over, let me see, yeah, over this 1455.79, and the answer is actually negative, R is negative 0.969. Okay. Now, so you see your R, it's negative 0.969. I mean, this is a negative. If you round this number here, this is negative 0.97, right? And this is very close to negative 1. I mean, negative 0.97, this is very close to negative 1. So R, so conclusion here is that our R is very close to negative 1, right? Negative 0.97 is very close to negative 1. And when you are close, very close to negative 1, remember, guys, we said if your R is very close to negative 1, you see here, we said if R is close to negative or positive 1, then we have a linear correlation. And of course, if it's negative, then it's a negative linear correlation, right? So here we have a negative linear correlation, right? So because R is very close to negative 1, so we have a negative linear correlation. Okay, and what does this mean to have a negative linear correlation, right? Negative, it means we have like a line which goes down, and it means that as X increase, Y decreases. Okay, so what's X? X is supposed to be, remember, we said X is the number of, the X is supposed to represent the number of police officers on duty, right? X is the number of police officers on duty. Y is supposed to represent the number of muggings, right? So what we are saying is, as X increase, Y decrease, Y goes down. Our line, our linear correlation goes down, right? So as X increase, that means that as the number of police officers increase, the Y, which is the number of muggings, decrease. Okay, so what we are saying is, as the number of police officers increase, right? That's my X. X is the number of police officers. The Y, that's the number of muggings, right? So then what we are saying is, as the number of police officers increase, the number of muggings, Y, decrease, right? So the number of muggings decreases. Okay, so that's the relation of the correlation between our variable X and our variable Y. Okay. All right. So again, I'm gonna write down again the formula for R, because I know it's a big formula actually. As I said, like in practice, like in the homework or the test, I'm gonna just give you the, all you need to complete this R. So let's have another example. Okay, exercise or example. Exercise. Okay. So I guess I'm gonna do a problem from the textbook. Let's see here. Okay.
Wow, this is so much information.
I know.
This is crazy. I got lost.
Yeah, I know, I know, I know. That's normal. When you do this like first time, it's normal. It's normal to get lost. I mean, it's normal. But what I'm gonna do, I'm gonna do another example. Okay, and in this example, I mean, as I said, in practice, you won't have to do all these steps. Okay, so I'm gonna show you an example. So what happens like in the homework or in the like in the test. Um, um, so yeah, so let's do another example. So so this is from the textbook. This is from the textbook. Textbook page exercise, I think 14, page 160, exercise 14. Anyway, 14. All right, so we have this data pairs. So the data are based on information from domestic affairs. But anyway, so the axis, that's the average. Let's say axis represents the average number of employees okay in a group health health insurance plan, and the Y, let's say that's the average cost as a percentage of claims. Percentage of claims. All right, so we have, again, we have two variables, let's say here, X, Y, and we have, let's say, just a 5 data pairs, okay, 5, just 5. 1, 2, 3, 4, and 5. So here, let's say you have fee, this is 40, here it's 7, this is 35, let's say here 15, and 30, this is 35, and 25, 75, and 18. All right, so first, so question 1, you need to check that the sum of the x's is equal to 135. The sum of the x squares is equal to 7,133. Sum of the y's is 148. Sum of the y squares is 4,674. And then the sum of the x times y, that's 3,040. Okay. So you don't really, if you get the, I mean, you see here, I'm giving you the answers to the to at least 5 steps, right? Sum of the x, sum of the x, sum of the x square, etc., etc. Now, once you have these numbers, then you can compute R. So number 2, compute R. And in R, so I'm gonna just write down again the formula for R. So we said this, the formula for R is like, so you know, you have the sum of the n, you know, n times, so n times the sum of you know, the sum of the x's, so sum of the x times y, minus there's the sum of the x's, sum of the y's, over, and then you have like square root of, and then there's like this n, sum of the x squared minus sum of the x's squared times, so this is your R. The y squared minus, so then you have the sum of the y squared. Okay, so like you see here in this example, like this number, this sum of the xy would be this number right here. You know, sum of the x's, this one here, sum of the x's like would be this number, right? Sum of the y's. So this y's would be this number right here. Okay. And of course, that's the size of the sample. And then here, there is this sum of the, you see this sum of the x squares? And that will be this number right here. And then same thing for the y, of course, there's this sum of the y square right here. Okay, so that's this sum here, right? And all you have to do, guys, actually, it's you have to plug these numbers in the formula and then, of course, compute R. Okay. So in some sense, like in practice, like in the homework on the test, you just, you know, the answers of like the first 5 steps are given. Okay. And all you have to do is just to plug these numbers in the formula of R. But as you can see, I mean, the formula of R is not easy one, right? So we're gonna need some practice anyway. All right, guys, you know what? I'm gonna stop here, and tomorrow I will come back to this example because I need to explain again how to compute this R, I guess. Okay. All right, so I'm gonna stop here, and thank you for listening, and hopefully I'm gonna see you tomorrow.
Thank you. Did you do
Professor. Have a nice
attendance?
Yes. Yes.